Welcome to our graduation thesis presentation. The topic of our thesis project is automatic surface defect identification of steel plates and 3D topological mapping. Our team is composed of me, Radin Baghi, responsible for laser sensor interfacing and GUI design, Uğurcan Yıldız having the task of motor control and path planning, Oğuzhan Ersoy designing the mechanics and the GUI, Cuvan Hadi Kanbur responsible for registration and 3D reconstruction. The project is under consultancy of Associate Professor Hüseyin Ümit. Due to the developing and advancing life conditions, quality and safety in the industry around the world is becoming more and more important. Although the production techniques are advanced and produce almost flawlessly, there may be problems such as pimples, dents, and scratches in the parts produced due to the uncontrollable reasons. The project aims to create safer environments by detecting errors quicker and more precise in the production line. With the developing sensor technology, it is possible to detect defects on part surfaces with more detail and accuracy. This method can be considered as a functional solution for the quality control processes. Our motivation is to develop an up-to-date and autonomous system to detect defects on the parts and make a way to leave traditional methods for this problem. This system, with its high precision and reliability, provides the ability to detect defects in micro-dimensions. Also, increasing efficiency and decreasing process time are the other advantages of this system. The system is designed to be able to design and installation of the Cartesian robot, complete scanning of the parts by the laser scanner, processing of data acquired from the laser, monitoring the detected defects on the interface, 3D reconstruction of scanned parts, and detection and localization of defects of the parts. Motor speed here needs to be constant at 30 millimeters per second to be compatible with the feed speed of the laser profile. The maximum area that can be scanned here is 30 times 30 centimeters. The distance between laser and part needs to be held constant at 53.5 and 78.5 millimeters. For a reliable result, the system needs to have minimum vibration while moving over the part. 4-axis moving ability provides access to all surfaces of the part.
After the mechanical system design course, some changes had to be made in our design and technical requirements. First of all, workspace of the robot reduced to 30 times 30 centimeters. Also, axis number of the robot reduced to 4. Due to all changes, motor and drive wheel calculations has been made and new components are chosen. Here, our new mechanical design can be seen. In order to perform a precise defect detection, scanning has to be flawless. In a new design, our 4-axis will help us to have good scanning result with its movement capability in 4-axis. Reflections are one of the biggest problems for the scanning process. To reduce reflections, a black platform is attached at the bottom. The black platform absorbs the light reflected and gives us more accurate scanning results. Power transmissions are made with power screws and belts. Lastly, hardware components of the system are listed. 4 NEMA 17 stepper motors are used to control the movement. The key component of the system is scan control 2910-25 laser profiler sensor. Also, TMC 2208 step motor drivers are used. As a controller, STM32F103 will be used.
This section of our presentation includes system flowchart, system block diagram, and GUI design. First, let's look into the system flowchart. The motors in X and Y axis start to function in predetermined model until both limit switches are triggered. This sets the 0 point for our scan. For orientation of the laser, data gathered from laser itself will be used. Special path is needed for each unique part to be scanned, so users should determine the path to be followed by laser. Laser starts its path and begins transmitting data to computer. Each point data received by the laser is multiplied by the transformation matrix and transferred to the global coordinate frame. After the completion of the scanning, 3D visual of the part is constructed in user interface's graphical screen. The CAD model of the part is placed on the point cloud data so that they are in the same coordinate plane. This operation is called registration. When this process is complete, 2 point clouds are ready to be compared and detection can be made. System block diagram is visualized in the slide. As you can see, a small demonstration of the scanning process can be seen in the bottom right corner. We found it appropriate to design GUI over the Qt framework due to its speed, ease of communication, and usefulness. GUI is where the CAD models are selected, paths are defined, and the 3D data construction is made. Besides, user can also access to the laser's configurations in GUI.
Hi, I'm going to talk about 3D reconstruction and registration methods that we plan to use in our project. As my friends mentioned, we need to scan the whole surface of the part with laser sensor for accurate 3D reconstruction and comparison. However, with the raw form of these measurements, accurate 3D reconstruction is unfortunately not possible, because every profile data obtained as a result of measurements is in the current coordinate frame of the laser sensor. We need to transform all points from the laser's coordinate frame to the fixed coordinate frame. To do this, we need homogeneous matrices at each measurements that created with the laser's orientation and translation values according to the fixed coordinate frame. Then by multiplying each point with these matrices, we transform the points into a fixed coordinate frame. Registration can be summarized simply as bringing the scanned parts point cloud and the reference point cloud to the same coordinate frame. We need to do this in order to get successful results in the comparison that we will make in the defect analysis. As you can see on the left, our laser positions were different in 2 measurements. It's not possible to make any comparisons between these 2 point clouds with the first version. That's why we need registration. First, we test on a sample with the iterative closest point algorithm, which we mentioned in our mechatronic system design studies, which is widely used in industry and still being developed different versions of it. You can see the result of ICP on the right. We think there could be 2 reasons why the result of this alignment is failed. Firstly, we observed that the initial transformation for ICP is not successful in our current situation. Additionally, unwanted visualization is and calculations occur when we get the background in our measurements. When we tried to set a simple threshold to remove background, we couldn't get an accurate result in parts that are not too high from the ground. As we know from the laser sensor features, which has a CMOS sensor, we can get intensity values for each point. In the ongoing process, we plan to remove background with intensity differences. Later, we got much more successful results in the same sample with RANSAC-based global registration method. We know that we can get 1,280 points per profile with our laser sensor. While we only need the transformation matrix for alignment, we downsample our source and target point clouds because there is no need such high resolution. Then we transform our source and point cloud with transformation matrix obtained by the global registration method. You can see that successful result is obtained with the point cloud, which appears as a single scan on the right. As I mentioned before, we plan to reduce redundant computations in our future work by removing the background. Now you can see our work plan here. After the scanning and registration algorithms, we need to update the first version of the user interface. At the same time, we have the necessary infrastructure and for the defect detection application, and finally, our final test and report come after that. Thanks for listening.